So I want to talk about a correspondence between the Teichmüller space and the Segal moduli space. So the Teichmüller space is an L infinity, a space of L infinity deformations of the complex structure. I'll define everything very carefully as we go along. What I mean by L infinity, I have to make some things precise, but it's referring to the Beltrami differential, which I'll define. And it's a Banach manifold. And the theory of the Teichmüller space was developed by Hausdorff and Burst and many other people in the 60s. A couple good references are Leto's book and Nogg's book. They're a bit old, but in some ways they're the best in my opinion. So the second space is the Segal moduli space, which maybe is what's of interest here. And so that's a space of Riemann surfaces together with boundary parametrizations. And so then you want to model by an equivalence relation, so conformal equivalence, but it has to preserve the boundary parametrizations. And a bit of history of it. So Frieden and Schenker started thinking about the moduli space of punctured surfaces in association with the conformal field theory in '87. And then Baffa introduced these local coordinates, what he was calling local analytic coordinates around the punctures in '87. And then Segal had this infamous preprint with the sketch of conformal field theory in which more or less equivalently you can think of the surfaces together with some boundary parametrizations. And then in that setting, people tend to use smooth or analytic, like complex analytic boundary parametrizations. And then David Radnell and I started using quasi-symmetric parametrizations, and so I want to explain why. So David was given by Iji the problem of solving some analytic problems regarding the Segal moduli space. For example, sewing should be holomorphic. We also want the determinant line bundle to have a holomorphic sewing operation. And then completions are also important. So in investigating that, we realized that the quasi-symmetric parametrizations were important. And the reason is, if you do that, then you discover that these two spaces correspond to each other. So after this analytic completion. So they're essentially isomorphic, but you have to just mod out by a discrete modular group. This is in the special case that this surface sigma is a bordered surface, so it has to be a genus G surface, finite genus, with n boundary curves. Specifically, they have to be borders, that's a little stronger, that are homeomorphic to the circle. So if you make that assumption, then it's possible to show that these two moduli spaces are the same. So there's two things going on. One is there's this analytic completion, so that's an analytic result. And if you have that, then you can deduce a number of things about the moduli space. So for example, you have a complex structure, sewing is holomorphic, a bunch of things that you need, apparently for the definition of chiral conformal field theory. But secondly, and I really want to emphasize this, sort of independent of this analytic result, so that it's a collection of results that show that this completion is natural. But we also have this geometric fact that these two spaces are the same. And so that has a lot of consequences. So for example, if you have some theorems in Teichmüller theory that tells you some things about conformal field theory, and it also goes the other way. So you can get theorems in Teichmüller theory from ideas in conformal field theory. I don't know if I've used a theorem yet in conformal field theory, but I've used the picture. Okay, so that's the first part. So today, it's the top row. I'm hoping, I don't know how well it'll go, I'm hoping to talk about the Teichmüller space in the first hour, and then the Segal moduli space and the correspondence in the second hour, and talk about how this arrow works. So that's today. So I promise, some people came in and saw me writing, said, oh, I hope you're not going to go too fast. So I promise not to go too fast. So let me stop and see if there's any questions before I describe the bottom half of the board. Okay, I'm not seeing any questions. Okay, so the bottom half of the board. So when this really interesting monograph of Taktajan and Teo came out, somehow, you know, we saw this and we're sort of electrified by all the great results in it. And somehow it seemed really natural. Also, you look at the earlier work of Knox Sullivan and a whole bunch of things in the literature, and sort of you get electrified. You see that this Weil-Petersson class is very natural. And so then you say to yourself, is this really the right completion? So do we want to complete the quasi-symmetries? Now, just to be clear, this is interesting on its own. This is a classical space. No one in its invention knew anything about conformal field theory and somehow invented nearly the same space. So this is interesting on its own without thinking about exactly what the completion is. But then we sort of thought, based on various things, which I hope to talk about the next time, that the Weil-Petersson class boundary parametrizations are somehow maybe more suitable for CFT, or at least for some things in CFT. So, but at the time that we realized that, the Weil-Petersson Teichmüller space wasn't in existence, except in the special case of genus 0 and n equals 1. So then we had to sort of reinvent, or we had to participate in the invention of the Weil-Petersson Teichmüller space. And so our contribution was in the higher genus and the greater number of boundary curves. So the low genus, or zero genus in one boundary curve, that's the universal Teichmüller space, which is particularly important. It started with Guizhen Kui. The paper initially wasn't cited that much, but nowadays everyone is citing it, thank goodness. And there's another paper by Guo, Hui Guo. And then, of course, Taktajan and Teo's monograph, which came out on the archive in 03 and 04. And then, nearly simultaneously, Jana Gishida and David Radnow, Wolf Staubach, and I worked out the higher genus theory. And then once that's done, actually you can use the same quotient, because the modular group here actually exists in both spaces, and you can still take this quotient. And so this is, David and I did this shortly after we met. And this was with both David and I a while later. Okay, so that's going to be hopefully the second part of the talk. Or, you know, and I think that some of the applications in the first half might end up spilling over to the second half, because I really don't like rushing. Okay, so now that's the whole thing in a nutshell. As I said, I'm going to do the top row today. Are there any questions about this?
So what is the connection between the top and the bottom?
So
roughly.
It's which completion you choose. So in the top,
so there's no like a containing or
oh, I see.
quotient or whatever.
It's not a quotient, it's a containment.
Okay.
Inclusion is holomorphic,
Okay.
but it's not. It doesn't sit as a submanifold.
Okay. Okay.
Anything else? Okay, so now I don't know everyone, so I don't know how much I should be saying. So if I say, I suppose I should define quasi-conformal map, but one of the things is I don't want to do too much technicalities. This is kind of awkward, isn't it? I should have used this board first. What do people do? Oh, I see.
Goes pretty high.
Okay.
I guess we will interrupt if we need to.
Sounds good. Okay. So so let's see. So the top square by itself would be a reasonable half course in a graduate course. So I really need to skip a lot. I just want to give the basic ideas. Obviously, I can't prove a single thing, but I can sort of, if anyone's interested, some things I can do some things that can't, and I can at least point to the references. Okay, so let me start with the definition of Teichmüller space. Actually, I can't resist. So the relation between these two spaces, I find really interesting. I can give an analytic answer very fast, but what does it mean in CFT? I've been asking that over and over again. I don't know. It's a good question. So I have some ideas, but they don't fit in this mini course. So let's fix a Riemann surface sigma. So the Teichmüller space, T of sigma, it's a set of deformations. Let me just explain this. So F, you fix a base surface that sort of determines the type that you're thinking about, essentially what's called the conformal type. Oops. So this is a quasi-conformal map. I'm going to define that in a second, because I saw someone nod, so I better define it. And then you have to mod out by a certain equivalence relation, which I'll say in a minute. Okay, so the technical definition of quasi-conformal map is it means that you have it's a usually orientation preserving homeomorphism. You do need to add some analytic conditions, and depending on your favorite ones, one of them, I won't say much about it, it has to be what's called absolutely continuous on lines, which means that if you...
the Riemann surface can have boundary sets, right?
Anything, yeah, anything. I was gonna, it's a little fussy when you talk about this equivalence relation, given the different types of surfaces. I'll just indicate what you do. So I haven't said this equivalence relation yet. So these are orientation preserving homeomorphisms, which are what it's called absolutely continuous on lines. You put a box in the domain, and it has to be absolutely continuous on almost every vertical and horizontal line. And once you have that, you have partial derivatives exist.
And this does not depend on parts?
No, it's a good point. You have to have this condition. And you have to have that the Beltrami, this is what's called the Beltrami differential. Maybe I should define that. This has to have L infinity norm strictly less than 1. What that condition means, it means that you have a deformation of the complex structure. So, if this were 0, then d bar would be 0. It's a complex analytic map. But if this is sort of allowing some distortion of angle, and this condition is that it doesn't distort too much.
Symbol is and? Or?
Yeah, that's an and. Okay. I can't do an and. I can't do many things, because I taught myself to write. So
This definition is basically the quotient.
the quotient, yeah. So it transforms, if you want to write in coordinates, it transforms like h of z dz bar over dz. So, and I wrote it with the Wertinger operator so that it makes sense on a Riemann surface, but in the plane it's just d by d, df dz bar, df dz. Okay, so now what about this equivalence? Oh, I should also mention quasi-symmetries. So, and I'm just going to say it's boundary values of some sorry about that, f from the disk to itself, which is quasi-conformal. And the boundary values are in particular homeomorphous in the boundary, but they're better than that. There's a whole bunch of equivalent definitions, but this is the easiest one to get off the ground. And I use this funny symbol. D is going to be the disk, odds of less than 1. And D minus is the outside of the disk. So together with the point at infinity. Okay. And you might say, why are you, this thing's in the way. You might say, why are you using the outside of the disk? It's just to sort of keep the same conventions as a bunch of things in the literature. So, okay, so now let me get this equivalence relation. So we have, if there's some, okay, what I'm about to say is a little bit of a lie. It's just a sort of quick definition, which is pretty much close to being right. If you want to get precise, you have to talk about, I have to introduce a bunch of things about Fuchsian groups, but I just want to say it kind of directly. So we have two cases that'll occur. It's enough for the intuition in this talk. So if you're covered by the sphere, in which case you're just a sphere, the plane, or D, and there's no boundary. Aside from maybe some punctures. It's not quite right the way I'm saying it, but I think it's the best way to get the intuition. And then we just say that sigma f sigma 1, f1 sigma 1 is equivalent to sigma f2 sigma 2, if and only if there exists a biholomorphism between the image surfaces such that F2 inverse of sigma of F1 is homotopic to the identity. Okay? Now, in the case that you're covered by the disk and there's some significant boundary, we say, we just replace, we have exactly the same equivalence relation, but you say homotopic to the identity rel boundary. Can I ask something? Does anyone, does anyone object to cursive? My cursive is much better, but I know not a lot of people grew up with cursive.
Fine.
This is very readable.
Oh, this is readable, is this? I'm just very slow when I print. So, all right. Okay, this rel boundary, it means that the homotopy fixes the boundary throughout, okay? So it is literally the identity, it is the identity on the boundary, but also throughout the homotopy. Now, if you think very hard, you'll realize why boundary parametrizations are going to be involved. This is exactly where boundary parametrizations get involved if you have some circles. So it's almost a very simple fact, but it's surprising that it just wasn't noticed. That's the way it is. Okay, so this is model 1 of the Teichmüller space. Any questions before?
F is just supposed to be quasi-circle inside, right? Not like at the boundary you don't.
Oh yeah, no, good question. So at the boundary, there has to be an extension to the boundary.
So basically, continuous or what type of extension?
So actually, what you can say is, if you have, okay, this is hard to say precisely. It depends on what kind of boundary you have. If it's a bunch of border curves, then it extends homeomorphically to the boundary. You can say that.
Okay.
No problem. If you want to talk in the general terms, which I'm kind of avoiding, because then I have to get into the weeds, but you lift the disk, and then you can always lift it in such a way that Well, when you lift it to the disk, it will have an extension to the circle. And then part of the circle will be an actual boundary when you pass down, and part of it is what's called the limit set. It's a bit complicated, but essentially if you lift, it's exactly that it extends to quasi-symmetry of the circle, which is a little better than homeomorphism.
When you define the quasi-symmetric as the boundary value, so you are saying that quasi-conformal from the disk to disk can always be extended to the boundary.
It can always be extended to the boundary. It'll be a homeomorphism, but even better, it'll be what's called a quasi-symmetry. I'm using this as a definition.
Yeah.
There's a dozen equivalent ones.
So and also the extension is unique.
No, that's actually the thing. So there are many, many extensions.
Then you need to choose one when you have some.
Well, so this is, I actually think this is a defect in Teichmüller theory. That you have all these different quasi-conformal extensions. You mod out by all of them. So, and then there are different kinds of nice quasi-conformal extensions. And there's different ones you can choose, but it's not unique. But see, somehow this equivalence relation kills all the non-uniqueness. So, yeah.
Do you mean that sigma does not see the commutativity doesn't have to hold on the boundary somehow?
Let me see if I understand it.
Like sigma is biolomorphic, but it's somehow you only look at if you have a boundary, you only look on the interior of the surface.
That's right, but also the homotopy means that the internal changes have an effect. So if F1 and F2 do something different to the internal homotopy group, then they won't be equivalent under sigma. And actually in the classical case, what most people think of when you look at the compact surface, what's going to happen is only the homotopy class is taken care of here. So F1 can be thought of as giving what's called a marking of the surface. So that's it's not a homology basis. It's a little more precise than that. It's a particular basis, a particular list of generators of the fundamental group. And so that's carried along by F. So yeah, part of it is boundary, part of it is that part. And you're anticipating some things later. So, okay, any other questions? Okay, so let me give an equivalent model. I gotta do this thing. No, I can't do it. Find the North American. How does it usually go? Do you take a break after 50 minutes or what is it? Or is it just kind of loose?
Yeah, 45 or 50. So.
45 to 50, okay.
You can also do after an hour and then 15.
Okay, I'll
As long as there's a 15-minute break.
15-minute break.
If possible.
Okay, so then I'll just stop at the first reasonable spot. Okay, so then there's an equivalent mu model. Just thinking about the pace and what I can remove. No, I'll keep this in. So we say L infinity minus 1, 1 of sigma is the set of negative 1, 1 differentials. So this is things that transform like, or locally they look like h of z, dz bar over dz in local coordinates z. Such that the norm is less than 1, modulo an equivalence relation, and then what you do is you say that T of sigma is isomorphic to the unit ball. Oh, sorry, I wanted the unit ball there. The 1 is for the unit ball. Modern equivalence relation, and then the standard definition is kind of cheating. So what you do is you just say mu1 is equivalent to mu2 if and only if, when you solve the Beltrami equation, so the Beltrami equation is, I don't know, let's see. Doesn't work.
Turn it on if you want to use that.
There it is. I don't know if you can see that red dot. That's the Beltrami equation. So you solve that equation, and there's a theorem on Riemann surfaces. There exists a solution, and you patch together local solutions, and it works fairly naturally. So we have to have that the solutions you get are equivalent in the original Teichmüller. They satisfy the original Teichmüller equivalence relation.
So the L infinity doesn't have there's two equivalence relations now. So, and L infinity is just a set, right? Or-
Yes.
So there you wrote also modulo equivalence, and then later again.
Oh, yes, thank you. Sorry, I was just blind. I just couldn't see it. Okay. Okay. Any other questions or corrections? Okay. I'm gonna put this. Okay. Let me just get this. Choose my examples carefully. I'm going to start with what if in this crowd. I think if you're familiar with this, you're familiar with the universal Teichmüller space. So let me talk about that one. So, and this is actually the Teichmüller space of the outside of the disk. You can do upper half plane or the disk, whatever you like. So that's the set. I mean, I've already defined this essentially, but I just want to observe that because you can always, the image is a disk, essentially, you can always normalize the target domain to still be a disk. So then you look at the quasi-conformal maps that take the disk to the disk, modulo the equivalence relation. And this occurs if and only if there exists a Mobius transformation, which preserves the disk such that F2 inverse of sigma of F1 is homotopic to the identity. I should say there exists, sorry, this is T, sorry about that. And then what we see is that this is just requiring that F1 and F2 agree on the boundary up to a Mobius transformation. And then what, that's because there's nothing going on inside the disk. It's topologically trivial, so only the boundary conditions matter. And so what you can say then is the Teichmüller space of the disk is the space of quasi-symmetries modulo Mobius transformations which preserve the circle. I just rewrote MoB. I wrote it as Mobius transformations preserving the circle. Maybe I should raise that a little bit. So then, this you can think of as a completion of diff S1 mod mob S1. So if you're thinking representation theoretically, this is, some completion. And of course, this is a symmetry group people are interested in. And then also, if any of you were at my talk, this completion is of interest when you want to think about when you have bounded symplectomorphisms on certain spaces on the circle. So it's sort of natural, even from other geometric and analytic points of view. Maybe that's the genesis of the idea. Nog Sullivan started this business, and maybe this is essentially what they had in mind. But anyway, so we have this interesting space. Unfortunately, it is not a Lie group, and stretching the notion of Lie group, it's continuous under right composition, but not left. And I think that's, according to Leto writes in his book, according to a suggestion of Tukia. Okay, so any questions about that?
The quick questions are, is there maybe an equivalent definition where there's some, for a quasi-conformal considered, one already fixes some normalization?
Yes.
Do you care about this here, or is it irrelevant for you?
Later I'm going to put in the normalizations, because if you don't put them in, it gets a little fussy.
Yeah.
In the end, I always like having modulos, what you're modding out, very clear.
Okay.
That's what I prefer, so I did it here. But later, yes, I'll put in normalizations. You could do that here if you like. So.
The norm S1 is just the boundary value of a norm D minus, is it?
Exactly. Yeah. Okay. Okay, I'm going slower than I hoped, but quicker than I thought. So that's, I guess, probably good. So now I want to move on to the lifted picture. And okay, I want to say a couple things about the lifted picture. So all of this can be done by lifting to the universal cover and then looking there. And that has certain advantages, especially if you're an analyst and you don't want to think about objects on Riemann surfaces. You just work on an open subset of the plane. And that's a perfectly reasonable thing to do. And it has all kinds of interesting things about it. It's nice to think about the cover. But I found that when trying to write the correspondence with the Segal space, it obscures things. So that's why I gave the definition in the way I did, which is equivalent to when you do it in the lifted picture. But now I just want to come back to the lifted picture because it needs to be done. So generically, I'm just going to consider the case when it's covered by the disk, though you can handle the other cases too. So let sigma be a Riemann surface. Covered by, and again, I'm using D minus. And then, so I'm just going to say sigma is equal to D minus mod G, where G is a Fuchsian group. Okay, I'm using some technical language here. Torsion-free Fuchsian group. And okay, what this means, okay, short version, if you don't want to know all the terms, which is a reasonable thing to do, especially in a short talk, it just means it acts discontinuously. So that this is a nice quotient. The quotient is a manifold. It's a Riemann surface. It's not a branch cover or anything like that. So, but specifically, if you care, watch out for the definition of Fuchsian group. It's not universal. One of them is that it's properly discontinuous, which is not quite strong enough. Torsion-free means that no element is, what do you call it? I forget what algebraists call it, but you take it to the power n and it's 1. So there's no element like that, and that's the only way you can have a fixed point based on some classification. So this means fixed point free, properly discontinuous, which is equivalent to discontinuous. The upshot is, this is a nice quotient, you get a Riemann surface. That's all really you need to know. So, okay. So, okay, so now I'm going to give a few equivalent definitions. So we can say QS normalized S1G. So here comes the normalization. So the N for normalized, I don't know if it's good notation. So we look at the set of phi, which are quasi-symmetries of the circle, such that it fixes, just pick your favorite points, I don't know, -1, I1, it doesn't matter so much, such that phi of G of phi inverse is a Mobius transformation for all G in your group. So somehow, you know, it sort of intertwines with another group. It induces another Fuchsian group. You can think of the set of elements of this, they actually introduce a new group. Then we can also look at invariant quasi-conformal maps, but of course, this is not unique, but you can look at some of them such that quasi-conformal self-maps of the disk, such that again, you take them to fix -1, I1, such that, and again, you have this intertwining property. So essentially, you're asking for this non-unique extension to still satisfy this invariance with respect to the group. And finally, we have the L infinity Beltrami differentials. So this is the set of mu and L infinity. Which satisfy invariance under pullback. Oops, sorry about that. So this is the condition that the Beltrami differential is invariant under pullback under Mobius transformations.
You want the unit goal?
Thank you.
I missed something. You said the extension is not unique in general to the boundary.
That's right.
So, but you impose that it fixes -1 I. So, but the extension has to fix. So here, if you're considering, so the map is defined on boundary.
Mm-hmm. I mean, I haven't shown the equivalence of these two
You're
things.
requiring that the extension fixes these points. Anything.
Oh, I see what you mean. Yes. This means that the extension fixes those points.
But it should be needed for any extension if you start from the thing that fixes the thing.
That's right. Yeah.
Maybe this is your.
But in fact, I haven't said the relation between these three. So there's no, since I haven't said the relation between these three, there's nothing to say except that there exists an extension to the boundary, and that one we demand that it fix the 3 points. Now to get what you were anticipating, if you start with one of these, its extension will indeed fix those 3 points. Conversely, if this one fixes those 3 points, it restricts to something in here. Yes?
What's the condition on mu on the last deference?
Sorry, what's the?
Condition on you.
What is the condition on mu on the last deference?
Oh, sorry, yeah, there's no equals sign. It equals mu. Sorry about that. Any other questions? Okay. I'm going to skip some things. So it turns out you can show these are the same. This is based on, so there's, first of all, it's not so obvious that there exists an extension. Like if you have something that satisfies this group property, why should you be able to find an extension that satisfies that? That was proven first by Tukia, and then later Aduadi Earl came with a more sort of geometric way of looking at it. To be honest, I should be careful saying that because I have not looked through Tukia's original proof. I'm just repeating what I read in other books. I do know the Doody-Earle construction. But okay, the upshot is, if you imagine that you can go back and forth between these, there exists some extension satisfying that. And this invariance property is more or less equivalent to this one. Takes a bit of work, but you can show that. And then, so by various people, again, still sort of classical, P of sigma can be identified with the normalized quasi-symmetries of the boundary, which are group invariant. And this is also can be identified with the quasi-conformal mappings, which are group invariant, modulo the equivalence relation. And this is equivalent to the Beltrami differential model. Okay, and so there's a bunch of technicalities and theorems to quote, and I gave you some of the names, the important ones. So that's the lifted picture, and I think I can make a good point of stopping. I think I need between 5 and 10 more minutes, but then it's a really natural breaking point. I think and then we can just.
Break whenever you
Okay. And then just make the second part shorter and maybe put some of it into the next. Okay. So now I want to talk about the Teichmüller metric. So. Yeah, then right after the break, I can start into the Segal moduli space, which maybe is a very good place to start. So let's say you have 2 points in Teichmüller space of some surface. And again, I'm sweeping a lot of things under the rug, just in the interest of giving the picture quickly. We need some sort of distance on the space or a metric on the space in order to get a topology. And what's usually done is the Teichmüller metric. So the definition looks a bit technical, but you take the infimum over all representative Beltrami differentials using the mu model of the space. I hope it's okay, I write it like this. If you have a point in Teichmüller space, it can be modeled by an equivalence class of mu's. And so by by this I just mean mu in the equivalence class. And you take the infimum of a half log 1 plus norm mu1 minus mu2 over 1 minus mu2 bar mu1. Infinity divided by 1 minus mu1 minus mu2 over 1 minus mu2 bar mu1. And so then you minimize this quantity. This is actually hyperbolic arctangent, if you like that kind of thing. And then it's interesting, actually, the resemblance with the hyperbolic metric. I've always found that curious, and I think it's not a coincidence. But this gives you a distance on the Teichmüller space, and it turns out with this distance, Teichmüller space is complete. Oh, I should say it's also a metric, so it's not entirely obvious it's a metric, but that can be shown. Okay, any questions? Oh, thank you.
I was wondering if this explains somehow why this is the universal Teichmüller space, because it seems like you can use this to embed.
Great question. Yeah, great question. So then actually you can think of them as literal subsets. And then that's how you get the complex structures on the more general Riemann surfaces, because it's easy to get it upstairs. So one way of getting a complex structure is using that. But there's some things to be done to show that this passes down to the surfaces. And I think, yeah, I'm going to do it. I'd like to finish off with talking about the Burrs embedding. It's somehow maybe one of the most important things. And then, you know, for people here, you sort of see this appearance of the Schwarzian, which is, of course, great importance to many people. So, Okay, so now this actually is best described in the lifted picture. You can do it in the non-lifted picture, but you have to prove the existence of a Schwarzian on the surface and what you mean by that. And it's a little bit not technical, but it's embedded in some abstractions. So I'm going to do this in the lifted picture where it's easy to state. So in the lifted picture, so again, we're just going to assume the Riemann surface is covered by the disk, modular Fuchsian group G. So then a quasi-conformal map F from sigma to sigma 1 can be written, I'm going to call it FL, from the disk to the disk, L for lifted, capital L, such that it satisfies this intertwining property that FL of G of FL inverse is the Mobius transformation for all G in the Fuchsian group. So I'm using that normalized quasi-conformal map. Oh, I should put the normalization in, but I'm going to use the mu's so it doesn't matter. It gets absorbed into the equivalence relation. So we get mu of FL of G times G prime bar over G prime equals mu of FL. And I need some spaces, so let sigma star be the double of sigma. So, and then we consider the space of quadratic differentials on the double. So at the moment I'm going to mention the two pictures together and then get back to the lifted. So this is B, which are quadratic differentials. Actually holomorphic quadratic differentials. What that means is you can write them as h of z dz squared locally. And of course on sigma. Such that a weighted L infinity norm with respect to the hyperbolic metric, I want here, is less than infinity. So that might look a little abstract, but if you lift it to the disk, it's familiar. I'll write that down in a second. So this is isomorphic to A2 infinity of D log G, and here we look at the phi, which are an A2 infinity of D, D plus now. Sorry, D. Such that G star phi is equal to phi. By this, I mean that if you were writing in local coordinates, h of g of z times g prime squared of z is equal to h of z in coordinates. On the disk, this L infinity norm is just, it's a quadratic differential, so you can't treat it as a function. You have to divide by some power of the hyperbolic metric. And so we get what we would say is that you get something like this. So that's the condition. And these are Banach spaces. Okay, I'm starting to think I was a bit ambitious, and maybe I should do the Burrs embedding after the break. I think I'm pushing it a little. It'll still take me another 5 to 10 minutes, so maybe it's better to do when we're fresh.